In this video, we'll just do a quick overview of some of the major non-covalent bonds. The first group I'll talk about is a group that we probably learned about in general chemistry, and that is ionic bonds. And in general chemistry, the probably first or major ionic bond you learned about was salt, or sodium chloride. And you can see that there's charges on each of those atoms, and because there's no number given, it's understood to be 1, so I'll just put a 1 there indicating that's a +1 charge on sodium and a -1 charge on chloride. So anytime you have a positively charged atom and a negatively charged atom, they can interact, and they are attractive forces. In biochem, one of the first places we really see ionic bonds, or bonds that will make these electrostatic interactions, are between an amine group, shown here, positively charged nitrogen on that amine group there, and a negatively charged oxygen on a carboxylic acid. And there's amino acids that have these two groups on them, and so amino acids can engage in these ionic bonds or these electrostatic interactions due to the charges, the opposite charges on those amino acids. If those two charges are identical, it'll give a repulsive force. If they are opposite, as they're shown here in this picture, they will give an attractive force. Now, to understand the next couple of groups, we have to take in a consideration here, in that some covalent bonds, and here's a covalent bond shown here where a nitrogen is covalently bonded to a hydrogen. In some covalent bonds, the electrons that are being shared in that bond are not shared equally. And so in this case, we can sometimes establish, or some bonding establishes, what's called a polar bond. And in this case, a nitrogen-hydrogen bond is polar, which means that the nitrogen group actually doesn't share the electrons equally with the hydrogen group, and it actually takes more of the electrons in the sharing than the hydrogen. And so because of that, because nitrogen's taking more electrons, it's a little bit more negative than the hydrogen. And so we use those Greek symbols I drew in there, that delta symbol, with the negative charge above nitrogen, indicating that that nitrogen is not a -1 charge or a +1 charge that we saw on sodium and chloride just a moment ago, but rather it is kind of negative. And the hydrogen, likewise, because it doesn't have as many electrons because nitrogen's taking more of them, is kind of positive. You can sometimes think about this, if you just to give you maybe a little bit different way to think about it, is that the nitrogen is not a full negative charge, but like a -0.5 charge. And the hydrogen is a positive 0.5 charge. Notice it's not a full negative charge and not a full positive charge. It's just kind of a partial charge. And so we call this a polar bond. And not when we draw structures, we typically don't show the partial negative and partial positive charges. So you will not see that in a normal structure unless they're really just trying to point that out. But nonetheless, if there's a polar bond, we can see these partial charges. Because of these partial charges, you can still have plus-minus charge interactions, just like we have with ionic bonds, except they're a little bit weaker because, well, they're not a full positive and full negative charge, or a partial positive and partial negative charge. So they can also interact in that way. So this allows us now, with that information, this allows us to understand hydrogen bonds a little bit. Hydrogen bonds are really specialized bonds, where if you have, and again I'm going to focus more on the biochemistry in situations that we see, but if you have an oxygen-hydrogen bond or a nitrogen-hydrogen bond, and we just talked about a nitrogen-hydrogen bond, those two types of bonds are polar, where the oxygen and nitrogen are partially negative and the hydrogen's partially positive. These hydrogens can hydrogen bond, and I'll just show those hydrogen bonds with little dashes, indicating it's not a covalent bond like we see between the oxygen and hydrogen. This is a non-covalent bond, or a non-covalent bond, and it's more specifically a hydrogen bond. And it can bind to a nitrogen or oxygen, because typically those will be partially positive. because of their situations. And so notice, I'm sorry, partially negative. Let me redraw that there. Those are partially negative because of, again, they like to steal electrons in a covalent bond or take more of them. And so now you have this partially positively charged hydrogen right here, and it's hydrogen bonding to this partially negative charge. Now that is not a covalent bond between them, that's a hydrogen bond between them. And likewise, the nitrogen-hydrogen bond that we see below there, that hydrogen, because it's partially positive, can also hydrogen bond to another nitrogen or oxygen, is where we typically see that. And again, it's just another, it's very similar to an ionic bond, but these are partial charges, and so they're a little bit weaker, and they also involve this partially positively charged hydrogen that forms that bond with a nitrogen or oxygen. So we call that a hydrogen bond. The next category is kind of this dipole-induced dipole category. And dipole is really, so I'll talk about each of them individually, then talk about how these can interact with each other. A dipole is pretty much like we just saw with the nitrogen-hydrogen bond or the oxygen-hydrogen bond, where you have a situation where you have a polar bond like this one here. So carbon-oxygen bond is polar, and in this case the oxygen is negatively charged and the carbon is positively charged. And that's always that way. If you have a carbon-oxygen bond, it's always a polar bond, and so we call that a dipole. Dipole sort of meaning it has a negative pole and a positive pole is one way to think about it. In some places we'll refer to this as a permanent dipole because this will never change. It's always that way. And if that molecule there that we're looking at that I just drew is going to interact with another one of the same thing, notice it won't interact like this. It won't organize like this because now the two negatively charged oxygens are very close to each other. In fact, what will really happen here is that the molecule, the second molecule, will actually organize differently to get the positives lined up with the negatives. And so you'll have a situation where with the second molecule, the positively charged carbon will be closer to the negatively charged oxygen. So those guys will be close to each other. So notice how these two molecules, this is what's called a dipole-dipole interaction because both molecules have a dipole, or both molecules have a polar bond that one has a negative charge and one has a positive charge on the atoms. And so it organizes these molecules to line up in a specific way so that unlike charges are closer together. Notice the two negatively charged oxygens won't try to line together, neither will the two positively charged carbons because they don't like each other. But the negatively charged oxygen and the positively charged carbon will organize to be near each other. So we call that, because both of those are dipoles, both those molecules I drew are dipoles, we call that a dipole-dipole interaction. So now we can talk about a dipole-induced dipole interaction. So in this case here, we'll reuse our polar bond that we just used in the last example, that carbon-oxygen one, and let's add in this carbon-carbon bond, or, remember these can be bigger molecules. I'm just really making them very simple. Carbon-carbon is not a real molecule yet. We would need more things hanging on it, but for the moment, let's just keep it simple. Let's say we have these two things that are going to interact with each other. A carbon-carbon bond is not polar at all. There's no partial positive or partial negative charges. Those two carbon atoms are going to share those electrons equally, and so therefore they will be very neutral. But remember, around an atom like a carbon atom, the electrons are flying around, and so they're always moving. And so there are times in which the electrons can move within the molecule a little bit and actually localize to one side of the molecule or the other side of the molecule. These are very temporary, but they can happen. Because again, electrons are negatively charged, and so they are moving around the atoms, and so they can move around. And you can think about this like kids in a swimming pool. You could look at kids and watch kids swimming in a swimming pool, and at some point during the day or during the time they're swimming, they might all congregate on one end of the pool. Electrons spread evenly around the pool are the way we kind of think about molecules, but really in molecules, the electrons are moving around, and therefore they might end up at one side of the molecule and versus the other side. Just like kids, they'll redisperse eventually, and so these are temporary localizations of a lot of electrons. When you have a dipole like this one, you have this negative charged oxygen, it might force a lot of the electrons that I'll show here in purple to congregate down on one end of the molecule. And so then you have this what's called an induced dipole, where this end of the molecule is kind of negatively charged, and this end of the molecule is kind of positively charged. And so notice that dipole that we have created is very temporary, and it was induced by the negatively charged oxygen. Again, these are pretty weak interactions, and they're very temporary because that induced dipole, these electrons will eventually spread back to the other end, and you'll lose this dipole that was induced. And so that can happen in a temporary sense. And so we call this a dipole-induced dipole interaction. But again, it's still the same as most of these non-covalent bonds we're talking about. It still has to do with intrinsically is a positive charge and a negative charge are attractive, and a negative charge and a negative charge are repulsive, and a positive charge and a positive charge is repulsive. Another version of this, as you could probably predict, is an induced dipole-induced dipole interaction. So in this case, again, we have two molecules, or in this case, I have two bonds that are non-polar. They don't have any partial positive or negative charges. But remember, these are like two little swimming pools, and eventually the electrons on one of the pairs might have all the electrons pile up down on one end of the molecule, as shown here. And so in this molecule on the left, we would have a partial negative charge because of that movement on that carbon and a partial positive on the other carbon. So temporarily, again, we have induced a dipole, a negative positive charge distribution amongst that bond. Again, very temporary. Eventually it'll go away, but for the moment it's there. And for that moment, the other molecule then will sort of respond to that, and it will have an induced dipole as well, where because of all this negative charge on this molecule here, the electrons on the other molecule will run to the other end in a repulsive fashion, leaving again an induced dipole in the second molecule. So the first molecule induced a dipole to the second molecule, and again, very temporary. Eventually those electrons will re-spread back out and average across each of those two carbons and neutralize it again. But for a moment you might get this interaction. And so in this case we call this an induced dipole interaction. Now, just to give you some feeling for the relative strength of each of these bonds, a covalent bond is very strong compared to an ionic bond. And when I'm referring to some of these bonds, I'm talking about them in the context of biomolecules like proteins and DNA. But a covalent bond, very strong, hard to break. Ionic, strong, but easier to break than a covalent bond. Hydrogen gets a little bit weak. Hydrogen bond gets a little bit weaker than an ionic bond. A dipole-dipole interaction is weaker than a hydrogen bond. Dipole-induced dipole interaction is weaker yet, and then an induced dipole is the weakest of all the bonds we just talked about. So organizing from strongest to weakest, you can see here on this page, gives you just some relative pieces to think about. The last type of non-covalent bond of major importance to biochemistry is the hydrophobic effect. And this is the idea where oil and water don't mix. And so that's really the way to think about it when you think about the hydrophobic effect. If you take oil and try to put it into a bottle and add water to that bottle and then shake it up, it will not make one continuous solution. It'll actually separate out into layers, where one layer is the non-polar layer, or the oil layer, and the other layer is the water layer, or the polar layer. So oil is very non-polar, and water is very polar. So things that are polar don't mix with things well that are non-polar. And in biochemistry, this is important because a lot of living systems are made up of water, but yet we definitely have some nonpolar molecules that we need to sustain living systems, and so therefore we have to interact or intermix the two. And so how does that happen? So therefore, because of that, the hydrophobic effect is very important. And all the hydrophobic effect is that if you try to mix something that's polar with something that's not polar, and you put it into a beaker, you're going to get two layers, where one layer is the nonpolar layer, and the other layer is the polar layer. And so this is a very dramatic effect where you can actually visibly see this effect by doing that experiment that I just mentioned a moment ago. And so when you think about things that are polar, well, we just talked about polar bonds. And when we see polar bonds, we see things like oxygens and nitrogens, like we talked about the nitrogen-hydrogen bond. We talked about the oxygen-hydrogen bond. We talked about carbon-oxygen. We looked at that one too, and we talked about all these things were very polar. They were polar bonds, and when you have a lot of polar bonds in a molecule, you become a very polar molecule. And think of one of the major polar molecules, or the major polar molecule is H2O, and notice it has oxygen-hydrogen bonds, which are polar, and so that is a very polar environment. A nonpolar environment or a nonpolar bond is one that doesn't have or doesn't create any charges or any partial charges. So the one I mentioned today in this video was the carbon-carbon bond, very nonpolar. Carbon-hydrogen, very nonpolar. And so just by knowing some of these bonds, we can tell which ones are nonpolar, which are these two. If you see a lot of those kind of bonds, you're talking something that's very nonpolar. And if you talk about things that are polar, you have things like oxygen and nitrogen in there as opposed to carbons and hydrogens directly. So the more oxygen and hydrogens you see typically, the more polar it's going to be in a very general sense here I'm talking. And nonpolar things are things with a bunch of carbon-carbon and carbon-hydrogen bonds. And so when you look at those molecules, you can sometimes very easily tell by looking at the molecule whether that molecule is nonpolar or whether it is polar. Nonpolar things love to mix with nonpolar things. Oil and oil mix as well. You mix them up together, it won't make two layers. If you mix up water and something made of water, and you mix those two together because they're both polar, they'll mix together. So if you mix two polar things together, it won't make two layers, it'll just make one. So if you have polar molecules in here and they're all polar, you're good. If you have a beaker and you mix two nonpolar things, when you mix them together, it won't make two layers, they'll be all mixed together. And so that's the idea of the hydrophobic effect.